Well, all right, welcome back. We've made it to the reading on hypothesis testing, a real highlight for us, and we're going to see that this hypothesis testing really draws on this confidence interval stuff that we looked at. They're very similar, so I want as we go through this, we can relate it to that we've already learned and hopefully make some sense out of this and make it pretty fairly easy or relatively easy for you to understand. So let's take a shot at that and talk first about the steps in hypothesis testing. So this just lays out kind of the scientific method that we use. First, we state the hypothesis, what we're going to test. And once we decide what we're going to test, then we need to figure out a test statistic that we're going to use. And one of the things we need to know is what's the probability distribution of that test statistic, because then that's how we're going to fail to reject or reject the hypothesis based on the test statistic. But we need to specify the level of significance, right? The level of significance is kind of opposite of what we had with a confidence interval. So if we've got a confidence interval that's 95% of the distribution, then we're going to say the significance of our test is 5%. And so keep that in mind. The significance level is just kind of the opposite of what we've done with confidence intervals. Then we're going to state the decision rule. Well, the decision rule is if our test statistic is larger than this or smaller than this or whatever, we're going to reject our hypothesis. And once we've got all that in place, then we collect the sample that we're going to use, calculate our statistics, and make a decision based on our decision rule and the value of the test statistic. And then finally, we'll make a decision based on the test results. That may be an economic decision, that may be an investment decision or something like this, and so that can be separate from the decision rule for the hypothesis, and we'll see why we might not make a decision based on significant results if they are statistically significant, but in some way too small for us to act on. So the hypothesis we're going to test, we call that the null hypothesis, H0 with our notation here. And one way to keep this straight for the exam is that the null hypothesis is always going to contain the equal sign in some way or another. So the null hypothesis could be have equal, greater than or equal to, or less than or equal to. And the alternative hypothesis down here, that's the one we are going to support if we reject the null hypothesis. Well, that's just the other side. So those may be not equal. That could be if one is greater than, if the null is greater than or equal to, then the alternative is less than. And if the null is less than or equal to, then the alternative hypothesis is greater than. So we've covered all the possible outcomes here. So the null hypothesis is what we're going to test, but it's really what we want to reject, because we don't prove anything with hypothesis testing. We're always making probabilistic statements. We're not making certain statements. And so we can reject or fail to reject the null hypothesis. That's all we can do. We don't prove it, but we can disprove it at some significance level. And as I mentioned, it always contains the equal sign. So the alternative is what we'd like to conclude, and it's what we conclude if we reject the null hypothesis. That offers support for the alternative hypothesis. So say we've got a portfolio construction criteria based on some factors, and we say, well, if we selected stocks based on these criteria and made portfolios, would they do better than the market on a risk-adjusted basis? And that's what we want to show, right? We want to show that our stock selection criteria beats the market. We do better in selecting stocks with this method. So we would set that up and say, well, let's do a null hypothesis that says our criteria doesn't work, that the abnormal returns we're going to generate with this portfolio selection method are 0 or less. And then the alternative is that they're greater than 0, that we are getting positive abnormal returns, or so-called beating the market with that portfolio selection strategy. So we'd set up the null hypothesis as less than or equal to 0, And if we can reject that, we would reject it because our test statistic is statistically significantly greater than 0, then we reject the null and conclude that, yes, our criteria does generate positive abnormal returns when we follow that strategy. Now, sometimes we may have a two-tailed test. If our null hypothesis is that the mean of our test statistic equals 0, then the alternative is that it's not equal to 0. Well, here's our mean, right in the middle here. And if we get anything close to that, we're going to fail to reject. We can't reject the null hypothesis if our test statistic is close to what we claim the mean is, in this case, 0. When will we reject it? We reject it if it's too high or too low. Well, too high or too low depends on our significance level, right? Here we've got a 5% significance level. So here's our confidence interval, or at least what we used as our confidence interval before, plus or minus 1.96 standard deviations either side of the mean. And we are going to reject the null if we're out in this tail, if we're more than 1.96 standard deviations above our hypothesized mean, or reject it if we're in this tail, because our alternative is just not equal to. So that's a two-tailed test, and the 5% significance, notice it's split between the two tails. If we've got 95% in the middle, we've got 2.5% in each tail. Now, one thing to keep in mind, and that we're going to build on in a minute, is even if this is true, let's say this is mu. Given the distribution of the test statistic, it could be out here even though the null hypothesis is true. But that's where we get the 5%, is we say, well, we're only going to be wrong 5% of the time if we use this rejection criterion. So that's important because we're going to talk about that later as the probability of rejecting the null when it's actually true. We're going to call that a type 1 error. And so the significance level is really that same thing. That is the probability of rejecting the null hypothesis when it's actually true. Now, sometimes we have a one-tailed test. When I described our abnormal returns test, I didn't want to talk about negative abnormal returns. I wanted to allow that, but we're going to test and see if they're less than or equal to 0. In this case, we've got a one-tailed test of greater than or equal to 0 versus a null hypothesis that it is, alternative hypothesis that it is less than 0. Or we could have less than or equal to 0 versus greater than 0. So what we've drawn here is a test, a one-tailed test at the 5% level of significance of that second null hypothesis. So our null is that the mean is less than or equal to some hypothesized value of the mean. I'll put mu here, I'll put mu 0, a specific mean estimate. And so when would we reject this null hypothesis? Well, we would reject it if our sample statistic is too high, but not if it's too low. A low value, we can't reject that the mean is less than or equal to 0. It could well be less than 0 if we get a value down here. When we'll reject is if we are statistically significantly above our hypothesized mean. So if we get a test statistic that's out in this area out here, then we're going to reject the null hypothesis. Now, why do we have 1.645 there? Because that was what we used for a 90% confidence interval. Remember, that left 5% in each tail. Well, this is a one-tailed test with a 5% significance level. So, given this distribution, if the mean is truly right here equal to our hypothesized value, 5% of the time we're going to get values out here just by chance and reject. So that's our 5% significance. We use 1.645 as our reliability factor, or 1.65, which we often use as well. I guess this is a little more exact, but the idea is the same. If we get more than 1.645 above standard deviations or standard errors above our hypothesized value, we are going to reject the null that the mean is less than or equal to 0, and this is our 0 point, that is less than or equal to 0, in favor of and offering support to the alternative hypothesis that our mean is greater than 0. So a test statistic is calculated from sample data and compared to the critical values to test the null hypothesis. Well, I guess we've covered that. If the test statistic exceeds the critical value or is outside the range of critical values in a two-tailed test, then we're going to reject the null hypothesis. So these critical values are very similar, as I've mentioned at least once or 3 times, to a confidence interval in what we're talking about. Now, I mentioned already type 1 error. It's the probability of rejecting the null hypothesis when it's actually true, and that was our significance level. How much room did you leave in that one tail or those 2 tails where even if the null is true, you'd still be rejecting just by chance because you got a high or low value that's out in one of these tails. Now, a type 2 error, failing to reject a null hypothesis. So if it's false, but with our test we fail to reject it, that's a type 2 error. And when we talk about the power of the test, we define that as 1 minus the probability of a type 2 error. Now, we're not going to be estimating, calculating type 2 errors. This is a concept, okay, rather than a calculation sort of thing. But 1 minus the probability of a type 2 error. Well, if your probability of a type 2 error is 90%, that is that 90% of the time when the null hypothesis is false, your test fails to reject it. Well, the power of your test then is low. It's 1 minus 90%. The power of your test is 10%. 10% of the time you get it right. You reject it when it's actually false. So a test can be quite weak in that. And the other thing we need to consider is there's a trade-off between a type 1 and a type 2 error. If you change your criteria, say you take your significance level to 1%, so you're talking about that 2.58 standard deviations either side of the mean, and you have very small tails out there with 0.5% in each tail, then you're very unlikely to reject the null hypothesis when it's true, but you're also very unlikely to reject the null hypothesis when it's actually false. So you have a higher significance level, but you have a lower power of your test. And that's always a trade-off, except in the case of if we can get more data points that we can use, then we could actually improve both types of errors. But other than that, the construction of the test involves really a trade-off between these 2 types of errors. Think of a jury trial where the null hypothesis is that the accused is innocent. So what would a type 1 error be? Rejecting a true null, it would be convicting an innocent person. What percentage of the time is your process going to convict an innocent person? A type 2 error is failing to convict a guilty person. And now you can kind of see the trade-off there. If we have rules of evidence that say, no, you can't beat confessions out of people, or you can't make them talk before you give them their rights, or any of this kind of things, these are all protections to keep the system from convicting innocent people, which we kind of have a bias and say, well, that's a bad thing. We really don't want to do that. But every time we tighten up the rules of evidence to reduce the probability of convicting an innocent person, well, that's the other side of the coin that we see. it makes it harder to convict a guilty person. So our probability of a type 2 error goes up as we reduce the probability of a type 1 error. So thinking of it in that way may help you remember it and keep it straight when you have to deal with it. Statistically versus economically meaningful result. Well, we can get statistical significance. If we've got a lot of data, okay, we may find, yes, that mean is statistically different from 0 at 5% level of significance. But then we look at the real value of those, say, abnormal returns to some portfolio selection criteria, and we see that, well, once you consider transaction costs, commissions, bid-ask spread, okay, once you consider the taxes that are generated because you're changing portfolios over the short term, same thing with transaction costs. If your strategy involves changing the portfolios a lot, you've got higher transaction costs. And so those costs and taxes may just swamp the small positive abnormal returns that you found. So even though they're really significantly, statistically significant, it's not something you'd want to pursue in practice. And another characteristic of this is risk. Maybe we looked at a 20-year period and we found statistically significant positive abnormal returns of 0.3% a year, or even 1% a year, which gets a little more significant, but the risk may be that that average was because there were 20% of the years were really good for this strategy, and the other 80% of the years it just slightly underperformed the market. Well, there's risk there, especially in the real marketplace. If you open up a shop using this strategy and promising these extra returns, in the first 4 years you fail to generate them, it's going to be hard to keep that client money and things aren't going to work out real well. So that may be what we call time period risk or even strategy risk. The strategy works, but it doesn't work all the time. And when it doesn't work, your clients get a little edgy, bail out, well, then it's not economically meaningful. It's not something you really want to pursue. Remember, the last steps in that portfolio or in that hypothesis testing list was first decide if it's statistically significant, if you can reject the null, and then make a decision based on those results. So here we're looking at that decision based on those results and saying, well, yeah, even though we have statistical significance, there's nothing economically there that we find particularly attractive as a strategy we want to pursue and invest our or our clients' money in. Okay, what's a p-value? Well, when we report a test, right, if we have a significance level of 5% and we say, oh, whoop, our test statistic was out in the tail, is beyond the critical value, we're going to reject the null. That doesn't tell you kind of how strongly you reject the null. And so what this p-value does is it's based on the actual result of your test statistic, and it says, what is the probability that we would have gotten a value this large by chance, right? When we set 5% significance, we say, well, if that probability is 5% or less, then we're going to reject. But the p-value actually tells you, and the way we've explained it here, we said it's the smallest level of significance at which the null could be rejected. Okay. So we can also view it as the probability of getting a test statistic that large just by chance, even though the null is true. So the p-value is going to get smaller the further out we are from our mean value or our hypothesized value. So if we reported a p-value as given 0.0213, that says the probability of getting this, a result that far away from the mean by chance is only 2.13. Now this could be a one-tail or two-tail test. If it's a one-tail test, we're talking about 2.3% in one tail. If it's a two-tail test, well, then that's 1.65% in each tail. So the p-value takes account of the type of test that you're doing. Now, if we get a p-value of 2.13, can we reject the null at the 5% level of significance? Heck yes, we would. And we can reject it at the 3% level of significance. But we couldn't reject it at the 1% level. So rather than just saying, yes, we reject at the 5% level, reporting this p-value of 2.13% gives us more information about how far from the mean our test statistic was, and it gives more information to the reader of the research, the user of the research. So here's our test statistic. This is just our standard normal. Okay? When we do a test of the mean, when population variance is unknown, use a t statistic. Well, that's our t statistic. It is very similar to our z statistic, except now we have sample standard deviation rather than the true standard deviation, rather than the sigma. And so there's our test statistic. So it is how many standard errors away from the mean is our outcome. If we know it, then we can use the z statistic. And remember, in an earlier reading, we had that table where we got into that. So here is just a little more general approach to that, where we're saying use a t statistic, and we've kind of ignored sample size here, which we paid a lot of attention to in the other reading describing when we had to use a t-test and when a z-test was acceptable because the sample size was greater than 30. So let's do a hypothesis test. We've been talking about it long enough. Let's see one. Let's test the hypothesis that a fund's mean return is equal to 1% a month. And let's test it at the 5% level of significance. So here's our data. The sample mean, 1.5%. That's our monthly return on our portfolio. The sample size is 45. Population standard deviation is 1.4%. And we think this population distribution is non-normal. That is, we can't confirm that it is normal, so we're going to have to treat it as non-normal. Well, with known population variance and a large sample size, we can use a z-test. It's going to be two-tailed because we're testing our null hypothesis is that the mean return is equal to 1% a month. So we're going to reject if it's significantly higher than that and if it's significantly lower than that. The critical z-values for a 95% confidence interval or a two-tailed test with 5% significance, that's our plus and minus 1.96 standard errors. So our decision rule, if the test statistic is outside the range of critical values, either tail, reject the null hypothesis that the mean monthly return is equal to 1%. Well, let's crunch some numbers. Where's our test statistic? Well, we got a monthly return on our portfolio of 1.5%. That is 0.5%, half a percent away from our hypothesized return, our null hypothesis of a return of 1% a month. Well, we know that's above it, but statistically, is it significantly above it? Well, it turns out it is. We take the population standard deviation of 1.4%, and we divide it by the square root of n to get our standard error right here, right? And we find that this result is 2.396 standard errors above the mean. Well, what was our critical value? Our critical value was 1.96, so we are going to reject the null hypothesis in favor of the alternative hypothesis that the mean return on our portfolio is not equal to 1% per month. Here we see a picture of that. We got our z statistic of 2.396. That is further out than 1.96. It's in this, we got 95% here, so what's in this tail? This is a 2.5% tail, and we're well into that tail. We're not in the fail to reject. You'll have to trust me, that's what I wrote. Fail to reject range. We're in the reject range. So we have critical values, and again, relating them back, that's the same thing. When 95% confidence is in there, if it's outside of there, we're only, there's only a 5% chance that we're rejecting this. when it's actually true. Okay, so that's our one-tail and two-tail test of the means. Those are the ones I want you to focus on. Get that straight, understand the pieces on there so you can't get fooled. Don't make it overly complicated. How many standard errors are we away from the mean? What's our significance level? Are we further away than that? One-tailed test at 5% has it all in one tail. Two-tailed test has 2.5% in each tail. Keep those things straight, and I think you'll be fine with the hypothesis testing. And don't say we ever prove anything. We reject or we fail to reject. So we've got some other tests, and here we're just describing the tests. You're not, notice the command words up here. That's what I'm trying to say. Notice the command words up here. Okay. Identify and interpret. It's not calculate. You don't need to memorize these formulas, but there's certain things about these tests that I think you should know, one or two things about each test that you should know. And so let's cover that and narrow that down, and hopefully you can leave this segment of the instruction with those ideas firmly in mind. So first one we want to look at is the difference in means test. Well, what the heck test is that? Well, if we've got two independent samples and we think they're normal, we believe they're normal, and we get the mean of each sample, and we want to say, gee, are the means of these two samples the same? This might be a test we want to do before we decide if we want to combine these samples when testing the mean, right? We talked earlier about adding data. Well, if I add data from another population and the mean is not the same, then it's not really going to help me in tests about the mean. But if we determine they are the same or can't reject that they are the same, then perhaps we can pool this data together and get some better results. Now, the denominator here, that's our statistic. Okay, to get our t-stat, we're going to look at this. And why is this a t-test and what's going on? Well, look what's in the numerator. It's very simple, very straightforward. We've got the mean of one sample minus the mean of the other. And our hypothesis is that this equals to 0, right? If mean x1 equals mean x2, we're certainly not going to reject equality. So that's one way to think about this test, is when would I never reject? Well, you'd never reject if they're equal. Well, then when would I reject? Well, if they're too darn far apart, right? If that number is statistically away from 0, then we're going to reject. So it's a t-test. We're going to interpret the results. Hey, if it's big enough, if this t-stat is bigger than our critical value, or in a two-tailed test, outside our critical values on either side, then we're going to reject. Now, we've got two formulations here, but those are just different denominators about how we figure out our, let's call it our standard deviation of the test statistic or standard error for the test statistic. In either case, we're saying, well, how many of these standard deviations from the mean are we? So, 1, it's a t-test. 2, the samples must be normal and independent. 3, if this number is too big or too small, we're going to reject that those two are equal. That's what I want you to take away from this test and this slide. So that's for independent samples. What if they're dependent? What if we're looking at weekly returns on integrated oil companies? So we're looking at ConocoPhillips and Exxon or BP or something like this. Well, we think that oil stocks returns are not independent, right? Because they're based on oil prices. They're based on expectations about future expansion of the national and global economy, right? Slowdown in China, we expect demand for oil to go down, prices to go down. This can negatively impact all these oil stocks. Now, they don't move in lockstep, that's for sure, but they are dependent. Knowing what one's doing tells me something about what the others are doing, at least on a probability basis. It sure does. So now we've got dependent samples, and we can't use that last test. We can't use the difference in means test. We use the mean differences test. So now we get weekly data for both these companies, for returns on both these companies, and what we're going to do is just look at each week and take the difference between them. We're going to look at all those differences and then we're going to get the mean of all those differences. Say we've got 100 weeks of data, we take the average difference. Well, if that average difference equals our hypothesized value, which if we're talking about equality, then this isn't going to be here, then it's just going to be 0, okay? This D with a line over it, that's the mean of the sample differences. Well, when would we really not reject the hypothesis that the returns are equal? Well, if that mean of all the differences was 0, we'd be hard-pressed to claim that the difference was anything other than 0. It is a t-test, and now the denominator is actually pretty clear. It's just the standard deviation of the sample differences over our month period, right? So now our statistic of interest here is the difference in returns monthly. We've got the standard deviation of those differences for 100 points. But now we're looking at the mean of 100 differences, so we're going to divide by the square root of 100. We'll divide by 10, and we'll be using just the straight standard error in the denominator. So the question becomes, is that enough standard deviations, standard errors away from 0 for us to reject equality? So that part's pretty straightforward. So identify and interpret, it's a t-statistic. The average difference across all the time periods are paired. That's why it's sometimes called the paired comparisons test. We pair them up by time period. We look at the average. Is the average significantly different from our hypothesized difference? If it is, we reject. What are the critical values? Well, in this case, degrees of freedom, if we had 100, degrees of freedom would be 99. We'd look at the t-table, determine our level of significance that we require, and if the null hypothesis is equality, it's a two-tailed test. We've got our critical values, and that's the mean differences test. So try and understand the differences between those two, okay, or be able to contrast those two, and that's the dependence and independence of the samples, okay, because we're assuming normal populations in either case for these test statistics to be valid. Okay, the learning outcome statement, as I mentioned, identify the appropriate test statistic and interpret the results for a hypothesis test concerning. So, reject if it's greater than the critical value, use difference in means for independent normal population, use the mean differences, sometimes called paired comparisons test, for two dependent equal-sized samples from normal populations. We've got a couple other tests here. This one, test of whether the variance of a normal population equals some hypothesized value, sigma squared 0 here, variance sub 0. And this is a chi-square test statistic. It's a two-tailed test. Reject if we're outside the critical values, either too high or too low. It's an odd test statistic in some ways. It's a little hard to interpret. We've got the hypothesized variance in the denominator. We've got the sample variance times degrees of freedom in the numerator, and that x squared, that's a chi-squared, that's a Greek letter, so that's our chi-squared test. So this one, I don't think there's too much to take away from it. I don't expect you to memorize that formula. I don't think it's required by the identify and interpret stuff. So if you want to test whether a variance is equal to a given value, then you want to use a chi-square test, and you want to reject if it's too high or it's too low. And if you're going to take one more thing away, it's some kind of ratio that we're looking at. It's not just the differences like we looked at in mean difference and difference in means. It's a ratio. It's distributed chi-square. Reject the null if it's too high or it's too low. And the null is what? That the true variance equals the hypothesized variance. So not a lot to take from that, but certainly there could be a straightforward question on the exam asking if you know that's a chi-square test, if you know that it's a ratio. Okay, test statistics for the variance. Now this test is a test of whether the variance of two normal populations are equal. So an equality of variance for two normal populations. It is an F test because the test statistic follows an F distribution. Okay. Now, the F test is a two-tailed test, but when you look at that F table in the back of the book and do a sample problem, it only gives us the upper critical value. What the heck's up with that? Well, which one we put in the numerator or denominator is kind of random, right? Which one we call sample 1 and which one we call sample 2. But the fact is, when, listen, as I said, it helps to step back and say, when would I not reject this? And that'll lead you to understand when you would reject it. Well, when wouldn't I reject it? Well, if the sample variance of both samples are equal, I wouldn't reject. How can you reject if both samples come up equal and you're testing whether the true variances are equal? So when do we not reject? We don't reject when that thing is 1. That F statistic is 1. We'll reject if it's too high above 1. We'll reject if it's too low below 1. But the thing is, let's say, let me just give you an example. Say we got 20 and 5. Well, that's a value of 4. We can assume that's pretty far from 1, and we could reject equality, at least under some pretty innocuous assumptions. We could reject it. And so we would be above the upper critical value. And I'm just making up a number, but let's say the upper critical value was 2.2. Well, we're above that. We're going to reject equality. We're too far away from 1. But what if we had just numbered them oppositely? Then we'd get 5 over 20. And so what I'm going to tell you now is, if we'd reject because 4 is too big, we would also reject because 1 over 4 is too small. And so that's why it doesn't matter if we get 5 over 20, we don't have the lower critical value. We just flip it over and say, yeah, but let's check that upper critical value and see if it's less than 4. If it is, we're going to reject equality. So we had variance equal to a given number. That's our chi-squared test, two-tailed test, reject it if it's too far away. This one, we've got 2 normal samples, and we take the sample variance of each one, and we're testing to see whether the true variance of both populations are equal. Okay, drawing toward the end here, let's talk about parametric versus non-parametric tests. Everything we've done so far is parametric tests. We've used the mean, or we've had tests about the mean, or tests about the variance, or equality of variances. All those things were all parametric tests. They're based on assumptions about population distributions and population parameters. Non-parametric tests don't make assumptions about the distribution, or at least few or none, and test things other than parameter values. And the examples given here are a runs test and a rank correlation test. A runs test is looking at a variable and if it goes up, next period you put a plus. If it goes down, you put a minus, and then you look how many pluses you get in a row, how many clusters of pluses, clusters of minuses. That's a run test to see whether you're really looking at randomness there. Rank correlation test, give an example of that might help. We do it with mutual funds, right? We know what a decile is now. It's top decile is the top 10%, decile 2, the next 10%. So if we ranked mutual funds based on their returns and put them each into a decile each period, let's say each quarter, or you could do each year, you get a long period of data there. And what a rank correlation test tests is persistence. If a mutual fund is in the top 10% in this period, decile 1, what's the probability that it'll be in decile 1 next period? If there was no persistence at all, it'd be 1 out of 10, right? Just random. If there's some persistence, it'd be higher than 10%. Well, it turns out it's fairly low. And this rank correlation test, we do test the correlation coefficient of its rank here with its rank here. Okay. If they're perfectly positively correlated, we've got lots of persistence. If they're negative correlation, it means being in the top, you're heading to the bottom next time. And if it's 0, it's just another random draw each time. But the point here being, we aren't using any parameters, we aren't claiming anything about the distribution, we're just actually looking at the correlation of the decile ranks from one period to the next to the next. Definitely a non-parametric test. Okay, well, any questions at this point? No? Okay. Well, then I think we can just wrap this up for hypothesis testing, and we'll see you next time.